we've now looked at just the definition and how we apply that definition. We said we're working with a constant force. Why? There's only one space to put F in. So you can't have a changing force. You have to have a constant force. So this is the unexpected thing in the definition. We're just going to remember that. Okay, and then we also said, remember that the work done is a scalar. So if it's a scalar, it's got no direction. And if it's positive, then you have to say energy is put in. And if it's negative, you say you are removing energy from the system. So we're up to there. So now what are we going to do with all this work that we worked out? We're going to use it to get the net work done. And what's important is there's two different ways to do this. And sometimes you get confused. So the two different ways is the first method that you can use is you can get the net work done by adding all the separate works that we've worked out now, by adding all of them together. So you work out the work done by gravity, by the frictional force, by every single separate one, and then you add them all together. So there you haven't used components at all. We use the whole force every time. Right. The second way, and this is the way that you will do if you were great with components in grade 11 maybe, is to work out F net. And then to use F net in the same equation, but now it's the net force, and just remember then the angle, you have to work with the net force's angle as well. So we're going to do one of these. Right. So you get the net work done by adding the separate ones, right? That's one method. Or working out F net first, and then getting from that the work done. Right. Now, let's do that. If you turn to page 12, I gave you there an example where we're going to do the two methods next to each other so that you can compare them. And don't say, I'm going to do the one or I'm going to do the other. You might prefer one. But when you get into the exam, they can force you to do a specific one. So by my wording, I'm forcing you to do things a specific way. So let's take the problem up there. A man pulls a 50-kilogram washing machine. I'm going to write my 50 kilograms there so I don't have to reread. Right. 3 meters up an inclined plane. So the displacement will be 3 meters. By exerting a force of 2,000 newtons. So I'm doing 2,000 newtons up the plane. That's the applied force. And it's parallel to the plane. Now, the plane makes an angle of 40 degrees. So that angle is 40 degrees with the horizon. And the washing machine experiences a frictional force of 20 newtons. Right. So everything they gave me in the question, I put into my picture to make it easier. Right, so let's go to the left-hand side. On the left-hand side with A, I ask you to draw a free body diagram. Is that the box or the dot? The dot, right. A free body diagram is free of a body. A little bit of grade 11 work slipping in. Eh? So you have to have a dot. And now I ask you to draw a diagram of all the forces acting on the machine, but no components, right? No components, just the forces. So what do we have? We have the applied force up the plane. We have the frictional force resisting everything that is down the plane. Right, what more? Normal force, nice. Normal force is always perpendicular to the plane. Right, and just remember, you may not make this into a horizontal, right? If they mark this in the end of the year and you made it horizontal, you get 0 marks, right? You have to keep it an inclined plane. If you've got problems keeping an inclined plane, make a small pencil inclined plane for you to work on if it's necessary, right? But it must still be an inclined plane. Right, and now we get to gravity. What do we know about gravity? The earth is not pulling you sideways, the earth is pulling you straight down. So the force by gravity will be straight down. Right, That was number A. I asked you to draw the diagram. Now number B, calculate the work done by every single force. So we have to take them separately. So let's start. And if you are working small, you can work here. Otherwise, you'll have to work on a separate page. Hey? So if you work small, you can work out the work done by friction. You can get the work done, by the applied force, the work done by friction, the work done by gravity, and also the work done by the normal force. Okay, I'm going to leave you to it, right? Work out the work done by each of those. Right, guys? Just remember, you have to check your calculators if they are on degrees. If you're not on degrees, you're going to have a problem. So you have to say shift and set up, and then check that you're with degrees, number 3. Shift, set up 3, just to make sure you are working in degrees and not radians or something else. Eh? Right, so the applied force was an easy one because it was acting in the direction of the movement and the angle was 0. Right. Then friction, also easy because that's just actually always in the opposite direction. Friction is opposing movement, so it will be always 180, and that will always be cos 180 will always be 0. So that one is removing energy. And then we get to the gravity, the difficult one. So for gravity, it will be the force of gravity times delta x times cos theta. Now, they gave us 50 kilograms. So remember, you have to multiply by 9,8. They're not working mass. Some learners don't distinguish between mass and the force, right? The gravity is the force. You have to multiply by 9,8. Then it's moving 3 meters. And now we get to that difficult one, which is telling me if you understand what's happening here. Now it's moving up the plane, right? So if you have working with gravity, which is straight down, you have to turn your pen from straight down until you get to the movement. So it's that whole angle, and we said that is 90 plus the bottom angle, that is 30 in this instance. Eh? Sorry? 40. Yes. Did I say 6? Okay. At least I wrote 40. Okay. 90 plus 40. Everyone all right? Okay. And then so you can write that, or you can write cos 130. Doesn't matter. I only write cos 90 plus 40 for you to remember where it came from. Right. And then if you work that out, what do you expect? A positive or a negative value? Will gravity be helping or hindering this movement up the plane? It will be hindering, so I expect a negative. So if you don't get a negative, you have to rethink everything, hey? So it's a negative. So there you get negative 944,90 joule, I hope. Right. Everyone happy? Can I see how many minus 944,90s we got? That's looking great, guys. That's looking great. Okay, and then we get to the normal force. So for the normal force, you have N is my force. Remember, you can put Fn or whatever, just specify. Delta x cos theta. And what do we know about, I'm not even replacing that. What do we know about theta when we're working with the normal force? You're putting your pen in the direction of the force, turning it, and you're turning it 90 degrees. And what do we know about cos of 90? That is 0. Right. So now we worked out the work done by every single force. And now we get to number C. C, I ask you use your previous answers to calculate the net work. So I'm forcing you to work with the first method, right? So the first method was I get the net force by just adding all the forces, all the work done together. So I get the net work by adding the work done by the applied force, the work done by the frictional force, the work done by gravity, the work done by the normal force. Right, what was the work done by the applied force? 6,000. Then I get to the work done by friction, that was minus 60. Then I get to the work done by gravity, minus 944,90. And then I get to the work done by the normal force, which is 0. Now, here I'm going to show you the first thing that makes it difficult for you when you get to the memos. When you go and work through old exam papers, for instance, sometimes it looks different from yours. The Department of Education exam guidelines say if something is 0, you don't have to show it. Right? If something is 0, you don't have to show it. I want you to show it because it means you've considered it and you have decided it is 0. So you might get to the memo and that part might be missing. Right? They are allowed to do that because they say if something is 0, then you don't have to put it there. So that might be missing. I would prefer you to put every force in there because then you consider every force, right? Okay, so we're up to that one and then you add it together and you should get 4995,10 joule. If you kept numbers in your calculator, it might differ a little bit, but that's what you're supposed to get more or less. Right. Remember, you have to have 2 digits after the comma. Right. 2 decimal places. Everyone happy with this? Okay. I actually think that's the easier method. Right? No components, not difficult thinking. The only difficult thing is the angle. If you can get that angle right, then this is the easier method to use. Right, but let's go and do the other method as well. So on the right-hand side, we start once again. Draw a free body diagram of all the forces on the machine, but now I ask you to use the components. So let's do this with components. So remember to keep it inclined. So F is fine, frictional force is fine, normal force is fine. But now for gravity, we are going to split it into components. So we're working with the gravitational perpendicular to, and we're working with the gravitational force parallel to the plane. So we're splitting the single gravity over there, we're splitting up into components. Now that's grade 11, so you're supposed to be used to doing this. Everyone happy? Right, that was A. Now we go on to B. Now with B, I ask you to calculate the net force. We're looking for F net. Now, net is the answer of all of the forces together. So we look at all of the forces together. Now first, let's look at this direction. You look at the direction that's perpendicular to the plane. Now tell me, is this washing machine going up into the air or into the block? No, it's not being pulled into the block. If you look at that one, it is not being pulled into the plane, it's not being pushed up into the plane. So if you look at that direction, the washing machine is actually standing still. Right? It's not moving in that direction, it's not moving in this direction. It's standing still. And if it's standing still, which law of Newton applies? First law, right? An object will remain stationary. Right. Okay, so in this direction, there is no net force, right? That means that what's working up and what is working down is cancelling out, right? They must give an F net of 0, all right? And if something gives 0, I don't even have to mention that if I'm working the net force out, right? So I end up with only looking in this direction because all the others together gave a 0. So I only have to look at that direction. So when I'm writing down the net force, I will say, okay, let's take upward as my positive direction. And then the applied force is a positive force. So I'm using the F for the magnitude and a positive for the direction. And now I'm looking at friction. I have to add them together, but friction is in the negative direction. It's a negative force. And then I'm also adding the gravitational parallel force, but once again, it's a negative. So that negative and that negative is because it's in the negative direction. So let me just repeat, because I know grade 11 was a long time ago. Those two made 0, so I can ignore them. Now I'm looking at what's left is that. So to get the net force, the answer of all the forces, I'm going to say F. It is in the positive direction, so I can take it like it is. But the other two are in the negative direction. So if I add them, I have to add negative F and negative FG parallel. Right. Now F we already have, so that's easy. I can put the 2000 in there for F. Frictional force we already have, that's minus, and that's 20. And then we get to gravitational parallel. Now, I remember grade 11 is a long time ago, so just on the left-hand side page, I just reminded you, right, if we're working on a parallel plane, we're working with X and Y. If we're working on an inclined plane, the one that's going to be split into components is gravity. And we're now looking at the parallel one. And how do I work out the parallel one? It's always the whole gravity times sine of the bottom angle. Right, so for this one, I will have the whole gravity times sine of the bottom angle. Right, and then you just have to calculate that. And for those guys who are fast, they already should have 1665,03 Newton. Okay, so is grade 11 coming back as well? Nice. Okay, let's go on with number C. Now we've worked out the net force, and what we're now going to do in number C is now we're going to use this F net to calculate the net work done. Right, so we want the net work done. Now for any W, it will be that F times delta X times cos theta. Now the net work, the net force, 1665,03, right? Then delta X, we moved it 3 meters. That is 3. And then once again, the angle might be a problem. What force am I working with? The net force. Tell me the direction of this net force. That net force was up the plane, right? It's actually perpendicular to the plane and up the plane. That was the direction of my net force. So I put my pen in the direction of the net force. How far do I have to turn it to get to the direction of movement? Nothing. So that is cos of 0. And then when you work that out, you also end up with 1995,01 joule. So it doesn't matter if you use method 1 or you use method 2. Right. So when you get to exam papers and you look at the memos, they might have done it this way, they might have done it that way. Both methods, perfectly legal. Both methods, same amount of marks. Choose the one with which you feel more comfortable. Right. So back to page 10. We are working on work. Now we've talked about the network, and we've worked out network with our 2 different methods. And now, for the first time, we're going to use that network. Why was it important to work it out? Because we now have a new thing that we call the work energy theorem. And the work energy theorem, we can actually just remember, and it's on the information sheet as well, that the net work done is equal to the change in kinetic energy. Right. Because we said the work done. If you got a positive work answer, it meant you added energy to the system. If you got a negative answer, it meant you removed energy to the system. And now we worked out the network, which is the total energy given or removed from the system. And you know energy can't be created or destroyed. So what happens to that energy? If you give energy to the system, what's the system going to do with it? It's going to go faster. It's going to increase its kinetic energy. Right. So the definition is easy. The network done on an object is equal to the change in kinetic energy of that system. And this is nice because now we have a way to get to velocities. Right. If you remember kinetic energy, down here, if you can't remember, the kinetic energy is half mv squared. Old news, grade 10. Right. So you have to put it in there. But what do you have to remember about the V's? The V's over there, remember energy is just a scalar. You don't have direction. So no positives and negatives, right? No positives or negatives on this side. That velocity is just magnitudes. Not that it's ever a problem, I think. I haven't seen one where it turns around. Okay, so go back to our problem. We are back on page 13 with our washing machine that is being pulled. Now what we did with the washing machine is we pulled it up and we've now worked out the network that we did. And it was a positive. What does that tell you? That we're adding energy to this washing machine's movement. So what's the washing machine going to do? It's going to speed up, right? It's going to have an increase in kinetic energy. So now in this one I ask you, the washing machine starts from rest. What do you get from that? That V initial is 0. Right, it's starting from rest, so the initial velocity is 0. And now I tell you, use the work energy principle or theorem to prove that after 3 meters, the magnitude of the velocity, so that's now the final velocity. Right, and I ask you to prove that the final velocity is this. Now just remember, if I ask you to prove it, you may not use 14,14. Right? It should be your answer. Right. I'm asking you to prove. If I'm asking you to prove it, you may not use it. That must be your answer. You must show that it is true. Right. So you're not going to use that. That is actually what we want to work out. We want to work out what is the final velocity. And then we can use it, then we can compare it to 14,14. So I'm leaving you on your own. You're going to do this. Is the change in kinetic energy, and that change in everything is final minus initial. Right. So both of them has got a half and an m. So what we usually do is we take the half and m out, and then you end up with v final squared minus v initial squared. Right. So go on with that to show that the final velocity is 14,14. Right. Is there someone who haven't found 14,14? You happy with that one? That's easy, eh?